So in multiple linear regression, there will be more than one independent variable, right? We used to have y equals to a plus bx, right? Now we will have x1, x2, x3, and so on are the independent variables, right? So you will have y equals to a plus b1 x1 plus b2 x2 plus and so on. This is what the new equation look like, okay? The computation will be tedious, so we will show in the R, okay? If the dependent variable y depends on independent variables x1, x2 up through xm, then the multiple linear regression line for the population has the form this. This is for the population, right? And this is for the sample. So when we do the R, do you remember what we did? We give some name, let's say A equals to, we did LM, and then you did Y versus X. That's what we did, right? But now what we do is A equals to linear model, and then you will do y versus x1 plus x2 and so on. That's what you do. That's the only difference you will be doing in this multiple linear regression, okay? Just to check that beta I equals to 0. There may be beta 1, beta 2, beta 3, beta 4, like that. So we will be testing for each of those beta I equals to 0. So what are the assumptions? There must be a linear relationship between the outcome variable and the independent variables. So this is exactly the same. We used to have only one independent variable. Now we have more than one independent variable, right? So this will be this must be a linear relationship between the outcomes and the independent variables. So we do the scatter plot of the residuals to see the linear relationship or curvilinear relationship. Curvilinear means non-linear, right? So multivariate normality is multiple regression assumes that the residuals are normally distributed, which is exactly the same as we had. Non-multicollinearity, it is different from the simple linear regression, because no multicollinearity means there is no relationship between x1 and x2 and x3 and so on, okay? No relationship between the independent variables. That's the non-multicollinearity means. And the last one is homoscedasticity, means the variance of the error or the residuals must be same along the all x values, okay? So the next thing we do is we will take an example in R and then C, okay? Multiple linear regression. So the stack loss is the built-in data, okay? So the this data is already in R. So what I'm going to do is I'm trying to run what is the stack loss. Stack loss data is basically the operational data plan for the oxidation and ammonia to nitric acid, okay? So how many variables are there? Airflow, water temperature, acid concentration, and stack loss. So here what we want to do is we want to take stack loss as y, and then we want to see whether y depends linearly on airflow, water temperature, and acid concentration or not. You see that? So stack loss data looks like this. See, you have 4 columns for that, okay? Airflow, water temperature, acid concentration, and stack loss. So this is the y variable, the last column, and these are x1, x2, and x3 variable, okay? That's what you were doing here. So linear model, y, and then wiggle sign, and then airflow plus water pump, water temperature plus acid concentration, and data is the stack loss, okay? Let us run that and then see the summary of that. What you see here is this is the intercept, right? So what does it look like? It is like y equals to negative 39.9197 plus 0.7156 x1 plus 1.2953 x2 plus minus 0.1521 x3, where x1, x2, x3 are these variables, okay? And then what do you see? Which one is more significant? So that this is statistically significant, less than 0.05. This is statistically significant, but this is not, right? So what do you say? As the p-value of airflow and the water temperature are less than 0.05, they are both statistically significant in the multiple linear regression model of stack loss. So also R square value is very good. You see that R square is how much? The residual standard error is not very big, but the multiple R square and the adjusted R square are almost 90%, right? So which is very good. And the p-value, you see the p-value? So this p-value is for all of them together, okay? The p-value is less than that, meaning that there is a linear relationship, okay? But if you see that one by one acid concentration is not linearly dependent. The stack loss is not linearly dependent for the acid concentration. But if you look at this separately, individually, these two are, this is not, right? So if you want to find out the 95% confidence interval for the response variable, then just you run this code exactly similar to the one. So for each of the y, predicted y value, these are the 95% lower limit, upper limit, and so on. And how about the 95% confidence interval for the beta value or beta value, basically, because beta value is for the population, and you're trying to find out the 95% confidence interval for the regression coefficient of the population, right? So for the airflow, this is the lower limit, upper limit. For water temperature, for acid concentration. So this is how we find out the lower limit and upper limit of that. You see that this includes 0, right? Whenever the confidence interval includes 0, you reject the null you do not reject the null hypothesis, meaning that there is no linear relationship for acid concentration, right? But separately they have. Okay. Now you want to do the test of assumptions. What you do exactly the same as above. We do the test of assumptions. You see that this is not very good. Why is that? Because the first one tests the linearity. Okay, so it is almost linear, not perfectly linear, right? Because it is close to the dotted horizontal dotted line. But it is not like perfectly linear though. It is just linear. Okay, you see that because if you see the normality test, it looks like it is normal, right? Perfectly. But here homoscedasticity almost close, but you see that little bit of increasing, but it stays the same almost, right? So it is almost on a line, and then but there are some influential point. You see that outside the 0.05 quick distance, so 21th data is outside that one. So maybe you should try to remove this data, okay, and then do all this process again. May give you the better feeding on this one and that one, and you will even get the better values of the better p-values, also better r-square values, better RAC values, and so on. Okay, so there are some codes I have put here. So one of the code is multiple linear regression with one or more categorical values. You see that? So are these data, all the data values were numerical, right? If there is one or more categorical values, so how do I do that? So the process is similar. So let me run that. This is the data support.csv data, okay, and I did my data. So that data is posted actually in the project 3. This data I asked you to pull that data from online, okay, so that's the same support data. Okay, so let us see the levels of the gender, male and female, okay, and there are 1000 observations, 35 variables under age, 2 levels under age. Okay, the support data is a random sample of 1000 patients from phase 1st and 2nd of support. Okay, so let us see the scatter plot of that support data. This is what you will get. So the age versus the total cost. Okay, age versus the total cost, and this is the linear regression line. So what is the code for that? I use slightly different, scatter.smooth, and I put x comma y. Okay, so you can, this is another way of plotting the scatter plot, doing the scatter plot. So it also automatically draw the line that goes through the middle. Okay, and let us do the what we want to do is we want to run the analysis. Let us see the summary. So the total cost is the y variable, right? The total cost is the y variable, and age and the sex are the x variables. What we see here is it is like a plus b1x plus b2y. Sorry, y equals to a plus b1x1 plus b2x2, right? That's what the model look like. You know that. And what do you think here? Yes, it looks like the age is significant for the total cost, but the sex male here, this is for sex male, okay? Sex is not significant. What does that mean? That means when the age increases, okay, when the age increases, then the total cost decrease basically, okay? So what do I say here? We got the total cost is this model, okay? So 6093.84 minus that times age minus this times male. That's what you get, because it says sex male, okay? This is the model you got for the male, okay? For the male, we will take male equals to 1. For the female, we will take male equals to 0. That's what we will do. All right. So age looks significant for the total cost, but the sex is not. For a male or female, 1 year increase in age actually decreases the total cost by 436. You see that? This is for the when you keep the age constant. So what it says is, you see that for male, okay, from here what you can see here is, for a male, 1 year increase in age actually decreases the total cost by 436. You see that? If age is say 60, and then you'll get one value, but if age is 61, then it will decrease by 436, right? Because it will be basically decreasing by 1 times 436.95 when you increase age by 1. That's what he's saying. On the other hand, keeping the age constant, total cost of male goes down by 38.92. If you said male, if you keep male is constant, then the total cost goes down by 38.92. Then female. So what does that mean? If you are taking about male, you will take this as 1. For female, this will be 0, right? So for female, the model will look like just this one. For the male, the model is the whole thing. If you take male equals to 1, then the total cost will go down by that number. But if you take that gender is female, that is male equals to 0, you will put for female, okay? In that case, the whole term will be 0. So the total cost will be up for female and down for male. So this regression model may not be a good model, as the R-square value is very small. You see that? The R-square is very, very small in this case, okay? So for male, that's what I was talking about. For the male, we take male equals to 1, and for female, we take male equals to 0. Thus for male, y equals to this, right? Which is, if you simplify, you will get that. You see that? Because this is a number, this is another number. If you subtract, this is what you will get. For female, similarly, you will get that one, because male equals to 0, and you will get just these two terms for female. Okay. Now we want to draw the linear regression line for male and female there. Let us do that. So we have, we want to see just one graph. What I'm doing here is plot my data age and my data sex equals to male, comma, my data total cost. And then for my data sex equals to male. So you can just copy and paste this. And I have some more. This is just for the good looking, okay? The main thing is that plot my data this and that up to here, okay? And if I run this, what does it do? It prints just the blue, just the male data, okay? For the next one, I want to put the female data in the red, okay? And also, let us draw a blue line for the male and red line for the female. You see that? The total cost is a little bigger throughout all ages. The total cost is a little bigger than in the female than the male, right? That's what we see from the plot. Okay, you see that? From the plot, we see that the effect of age is same in male and female. It's the same decreasing pattern, okay, for the cost. Also, the cost for male is lower than the cost for female, regardless of age, and the difference is same for all ages, okay? You see the exactly same difference between the cost of the male and female throughout all the ages here. This analysis assumes that the effect of sex is independent of age and vice versa. So, meaning that the age and sex are independent to each other. Called no interaction between the variables. Okay. Let us see the assumptions. That's what you will get. Okay. It looks like it is violating the assumption, because see, this is not normal. The residual is not normal, and also it doesn't look like the homoscedasticity here, right? And also the scatterness doesn't look good because you see that the red line is decreasing. It should not follow any pattern, right? And here the red line is increasing, here the red line is decreasing. So it looks like it does not follow the assumptions, right? So what should we do if the data set does not follow the assumption? So you can take, the one thing you can take is you can log transform, okay? If it doesn't fix, just remove those outliers, okay? These outliers. So if you remove a set of outlier, you will see another set of outlier. But you can check by removing some of the outliers and then see. You know how to remove the outliers. We did that before too, right? So this is the third row, 363rd row and 15th row. Looks like outlier here. Okay, so there is some more code if for multiple labels in a categorical data. If the categorical data have multiple labels, you can just look at that. All the description are given here.